again at the end of the video. With that being said, let's jump into some content. This week I'm going to be talking to you about continuous and continuity functions. Functions can be continuous and discontinuous, and you're going to have to be able to explain clearly why it's continuous or why it's not continuous. And I'm going to be highlighting some of the ways that we do that this week. This is a topic that becomes critical throughout Calculus 1. The continuity of functions is very important as we develop this course. According to our textbook, a function is continuous at an interior point C if the limit of f of x as x approaches c equals f of c. That's a really fancy way of saying if you can take c and plug it into the function and that matches the point on the graph and you get a nice clean value, then it's continuous at that point. So if you can plug it in and it works out, it's continuous. So that's the definition of it being continuous at an interior point C. So as you can read below, if you plug in the value and it matches the point, then your function is continuous. Doesn't sound that scary because it's really not. And moving on to the next screen. A function is continuous on a given interval if and only if it is continuous at every point of the interval, which again is a fancy way of saying if it follows a nice pretty line, you don't have any jumps, you don't have any asymptotes, it's a continuous function on that interval. And then a continuous function is one that is continuous on every point of its domain. Now, it obviously doesn't have any points outside of its domain, but if you look at a function across its entire domain, all the possible inputs, and you've got nice pretty outputs, nice clean points, and it follows a straight path, then you have a continuous function. Now, this doesn't mean that it's continuous for all real numbers, because not every function has a domain of all real numbers. So don't allow yourself to get tricked that easily. One type of question that you might see that tries to trick you with this is that you'll have a function whose domain is not all real numbers. And then they'll ask you which interval is it continuous on, and they'll give you all real numbers as one of your domains to try to trick you. Don't allow yourself to be tricked. All right. The continuity test is really popular for free response questions on the AP exam. This is one of my exam tips this week. The AP exam loves to give you a function and ask you to prove that it's continuous at a specific value. And it'll be a value where you look at it at first and you're not quite sure that it could be continuous there. If you plug in a value and you get something like 0 over 0, that means that there's a little more work ahead. So please, please, please make sure you take the time to read up on the continuity test in your textbook. This is something that your textbook does a great job with. I'm going to go over a summary of it really quick. If f of c exists, then c lies in the domain of f. Step 2, if the limit exists, then f has a limit as f approaches c. Step 3, then the limit equals the function value. So basically, if the point exists, then that c value is somewhere in the domain of f. And if that limit exists, then f of c, or f has a limit as f approaches c. So the closer it gets to f, the function has a limit. And then you just plug in your value and go. Moving on to example 1 is a function given continuous on the given interval, and they give us f of x equals sine of x over x on the interval negative 2 pi to 2 pi. Now, go ahead and pause and take a moment and graph that picture. So hit pause now. All right, have you taken a moment to graph this? Most of you probably reached for your graphing calculator and got some kind of crazy picture like this. Now, that scribbling in the middle, it's not just any old scribble. This goes towards something called an asymptote. This takes me to a very important exam tip. Your calculator wigs out like that because graphing calculators do not show asymptotes. They will not find those values for you. Instead, you'll put in something that has an asymptote and it'll give you a crazy picture like this. In this chapter, you will learn how to find what those asymptotes are and sketch it accurately, and I promise it's going to be worth the trouble to go ahead and learn how to sketch it the way the book shows you, instead of trying to look at this mess and figure out where the asymptote is. So since our graphing calculators don't show us asymptotes, but we can tell from the spaghetti on the screen that there is, in fact, an asymptote. This is a type of discontinuity, and it pops up right in the middle of our interval. So no, this is not continuous on the given interval. There is an asymptote. Now, as you guys will learn in this lesson, and even later on, you'll find an easier way to solve for this asymptote. You'll find that it's at x equals 0. So the function was not continuous. We can look at our picture, draw a sketch, and very quickly find a discontinuity. That means it's not continuous. Now on to example 2. This is a very common type of question to find on multiple choice. But I'm going to have you guys take it one step further and do the proof as well. That way you're prepared for a multiple choice question or a free response question. Now this asks us to show that the function given has a continuous extension to x equals 2 and to find that extension. What that basically means is they're admitting for you that there is a discontinuity and they're asking you to fix it. To start with, we're going to factor both the top and the bottom and see if we can simplify this rational expression. If we factor x squared plus x minus 6, we'll get x plus 3 times x minus 2. And then if we factor x squared minus 4, we'll get x plus 2 times x minus 2. So if we would like to reduce our rational expression, x squared plus x minus 6 divided by x squared minus 4, we can cancel out that common factor of x minus 2. That leaves us with x plus 3 over x plus 2. This is a much simpler version of what's really the same function. Now if we plug in our x equals 2, we're not going to get that nasty 0 on the bottom. We're going to get 2 plus 3 over 2 plus 2, which leaves us with 5 over 4. This takes me to another exam tip. I know you guys have a lot of those in here today. Your exam tip for this one: don't simplify. Don't turn it into a decimal unless you see your answer choices are decimal. More often than not, they're going to want the fraction. I know it's so much easier to plug it in our calculators and let it calculate the decimal for us, but I can promise you that you need to get used to using the fractions because more often than not, that's what your answer choice is going to be. It's also a very common mistake on the free response section for students to think they're simplifying to a decimal and do so incorrectly and get docked points. We don't want to get docked points, so unless the test specifically tells you to use a decimal, stick with the fraction. So now we have shown that the function has a continuous extension to x equals 2 because we were able to simplify our function and find that extension. We simplified our function, we plugged in x equals 2, and we found that that extension was 5/4. So we've completed